Hey everyone, welcome back today. Today we're going to look at topic 2.9 called the quotient rule. Yesterday or previously we've looked at a lot of derivative rules, including the product rule, which was used when two functions were multiplying. So the quotient rule is used when two functions have a quotient. In other words, when two functions are dividing. So the quotient rule of two differentiable functions f and g obviously can't happen when g of x would equal 0, because then we have a 0 in the denominator. But the actual rule itself is given here. Now some people write it like this. When I write it, I usually switch these two. So I would probably write it more like this, and this is how I always remember it. So you might be saying, what's the difference? There is no difference. There's no difference in how it's written and how I'm writing it, just how I remember it. So I always remember it as it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over denominator squared. So you only want to do this when you have two functions with variables in them, in both one in the top and one in the bottom, one in the numerator, one in the denominator. And you also can't simplify those. Because if you could simplify them without doing the quotient rule, it'd be a good idea. All right, so let's take a look at our first example here. Here's an example problem. Take the derivative of y equals 5x plus 2 over x squared minus 1. So we can see here we have a function of x over a function of x. There's no way of just splitting this and simplifying it. So this is a problem we would definitely want to use the quotient rule on. So let's take our derivative dy dx, or y prime if you prefer that. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. That's it. That's your derivative. If this is a multiple choice question, you may be asked to simplify this. If it's a written question, that would be good enough. But let's do some algebra simplification in case we would ever need it. So distributing the 5, and then distributing the negative and the 2x. And then combining like terms and writing it in descending order. But again, the answer up top there in the pink would be perfectly acceptable if this was a written question. Okay, example 2 says find the equation of the tangent line to that function there. Remember, what two things do we need to write any line, in this case a tangent line? A point and a slope. The point's given to us, which is great. The slope is not. So we'll have to find the slope of this equation, y equals e to the x over 1 plus x squared. So let's start with the slope everywhere, which is the derivative. And we will have to use the quotient rule again because there's no way to simplify that expression. So we have the denominator times the derivative of the numerator. The derivative of e to the x, remember, is just e to the x. Minus the numerator times the derivative of the denominator all over the denominator squared. Okay, if you want to simplify this, you can, but there's really no need to do that. So instead, let's just take the slope that we found, which is a slope everywhere, and find the slope at our point 1 comma e over 2. So we're going to put a 1 in everywhere we see an x. So it's 1 plus 1 squared, or 1 plus 1 times e to the 1 minus e to the 1 times 2 times 1 over 1 plus 1 squared squared. That gives us 2e minus 2e over 2 squared, which is 0 over 4, or 0. So that means our slope would be 0 at that point. So now we can write the equation of our tangent line. Y minus e over 2 equals 0 times x minus 1. But really, this whole right side would just be 0. So we're left with y minus e over 2 equals 0. Or if we add e over 2 to both sides, we get y equals e over 2, which is just a horizontal line at e over 2. All right, so here's example 3, and this is always a really interesting slide. We're going to talk about when to use the quotient rule and when to not use the quotient rule. Okay? Here's a quotient. We have x squared plus 3x over 6. So you might be thinking, I should use the quotient rule here. But really, no, you should not use the quotient rule here. You can rewrite this as 1/6 times x squared plus 3x. And that's just a scalar multiple of 1/6. So really all we got to do is take the derivative of the inside here. So y prime would be 1/6 times 2x plus 3. And if we distribute that, we would get 2/6 or 1/3 x plus 3/6 or 1/2. So our derivative would be 1/3 x plus 1/2. If you did do the quotient rule with that, you should get the same answer after you simplify it. But why do all that work when we can simply just rewrite it and differentiate? Same thing is true for b. You might be thinking, well, that's definitely a quotient, but we don't need to use a quotient rule for that. Let's start by rewriting it. I'm just going to distribute the -3 first. And right now it still looks like a quotient rule problem, but we've done these problems before without the quotient rule. So this gives us -9/7 plus 6x over 7. The derivative of that would be y prime equals 0 plus 6/7, or just y prime equals 6/7. Way easier to take the derivative of this than it would be to take the derivative of this. But in the end, you should get the same answer. Oftentimes in the AP tests, you'll have tables, such as this table of values here, and you'll be asked to do some type of differentiation with that. So here we have two differentiable functions, f and g, along with their derivatives, and then several values along the way. So the first question says, given h is equal to f over g, find h prime of 2. Don't even worry about h prime of 2 right now. We can't do h prime of 2 until we know what h prime of x is. So that's our first goal. F over g would be a quotient. So we have to use the quotient rule, which is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So that's our derivative everywhere. But now we want to find the derivative at 2. That's no big deal. We're just going to take x, and everywhere we see an x, we're going to replace it with a 2. Now we can go to our table for our values here. So h prime of 2 equals g of 2, which is 3, times f prime of 2, which is -1, minus f of 2, which is 4, times g prime of 2, which is 3/2, over g of 2, which is 3, squared. And then we can just simplify that. So we get -3 minus 6 over 9. Or -9 over 9, or -1. So h prime of 2 is -1. Here we have j of x, which is equal to g of x over root x, which is, again, a quotient which we cannot simplify, so we're going to use the quotient rule as, again, on this problem. So j prime of x equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, remember, the denominator is root x. And remember, root x is equal to x to the 1/2. So this would be 1/2 x to the -1/2. All over denominator squared. Now, before we find j prime of 4, it might be a good idea to rewrite this a little bit. So j prime of x is equal to root x g prime of x minus, and if I rewrote this second part over here, it would be g of x times 1, which is g of x, over 2x to the 1/2, or 2 root x. And that's all over root x squared, which is just x. And now I can take this derivative, which is the slope everywhere of j, and replace it with the slope that we want, which is x equals 4. Everywhere we see an x, it's going to replace it with a 4. So then j prime of 4 is 2 times g prime of 4. Look at our table here. G prime of 4 would be 1. Minus g of 4. G of 4 would be 5. Over 2 root 4, which is 2 times 2, all over 4. And that gives us 2 minus 5/4 over 4. 2 is 8/4, so 8/4 minus 5/4 is 3/4 over 4, which is 3 over 16. So j prime of 4 would be 3 over 16. All right, our last one here. The graphs of f and g are shown below and consist of line segments. Use the graphs to find each of the following if possible. So again, we have f and g on the graph there, and h is a function of f and g. So the first thing we're going to do is use the quotient rule to find our derivative. And now we're looking for the derivative at 0. So we're going to replace all these x's with zeros. Now we can go to the graph to find each of our values. So g of 0, this is g here, right? G of 0 would be 5. So we'll start with 5. F prime of 0. This is f. F prime of 0 would be the slope of the line at 0. So the slope of this line, you can see it's going down one, right one, down one, right one, down one, right one, down one, right one, down one, right one. Or you can use the slope formula, but either way, the slope would be -1. So f prime of 0 is -1. Minus f of 0, so the point of f at 0, which is 4. Minus the slope of g at 0, so the slope of this line. So we're going up 2, right 1, up 2, right 1, up 2, right 1, so the slope would be 2. Over g of 0 squared. G of 0 was again 5 squared. So that would be -5 minus 8 over 25. H prime of 0 would be -13 over 25. Our last one here, once again, we have w, which is equal to x squared over g of x. We want to find w prime of 2, so we should start by finding w prime of x. Denominator times derivative of the numerator minus numerator times derivative of the denominator over denominator squared. And now we're going to try to find w prime of 2. So let's replace all of our x's with a 2. All right, so g of 2 would be 7. So let's replace g of 2 with 7 times 2 times 2, which is 4, minus 2 squared, which is 4. And then g prime of 2. So the slope of that at 2, that's just a horizontal line. So that would be 0. Over g of 2 squared, g of 2 was 7, so 7 squared. So then w prime of 2 would be 28 minus 0 over 49. W prime of 2 would be 28 over 49. That does it for our look at the quotient rule. Thanks again for checking in, and we'll see you again soon.